Yeah, so is at the top? No, that's not the top. There's a little bit of explanation on the top. So the top I got that from Ravi, who gave me the equation in 2D, where you have a bunch of scalar field, and you have no mistake. Yeah, psi is meant to be actually a vector field dimension 2. I need to correct that. And then basically you want to solve this equation. The thing that is missing there is that this, at the moment, the way the collab is written is just on a circle. I think I've put an idea on the Zulip on how to deal with more than just circle, and I think Fabian, you had a similar idea, where basically you have a circle and then you can deform it by adding something which is proportional to, which is in the radius direction. That allows you to handle anything that looks like a circle, which is kind of a star-shaped circle in the sense that you cannot have like a bump. Everything is connected to zero, but it's at least something you can start with, and then you can see if everything converges back to the circle, which is what you would expect.
It's been so long since I thought about fluid in PE. So here psi is one of the functions we're solving for, and then that in some sense takes also the place of the angular coordinate, or this is only axisymmetric?
It is assumed to be axisymmetric. Okay. Psi is some kind of a string function. Right. So you reduce, because you are in axisymmetric coordinates, you can simplify, I mean, you can get a simpler representation and instead work in terms of a string function, let's call it like that, so that you don't have the vector field B anymore, but instead you work with C and a few other scalar functions.
And can we study, because some of the papers tie the existence of solution to symmetry, so
yeah.
Suppose we wanted to study the case without symmetry.
Right, but this is less than that. This is in the case of symmetry, where it is guaranteed that you can find the solutions. Right. Then this is a simpler representation. Right. Okay. So it's not like the solution of the full thing. It's just kind of even going on the opposite direction of trying a symmetric domain and then solving for the different parts of the fields.
Okay, just to be clear. Okay, good.
Yeah. So there's some way of training if you go down a little bit. So these are the definition of all of the fields. You have the definition of the equation here, and then there's so the function get HK and param. This is something that gives you all of the fields. I don't know if anybody knows haiku. So this is JAX. I assume that JAX is fairly standard. I don't know if anybody, yeah? This is using haiku. I guess the modern way is mostly Flax. I don't know what you guys use when you write. Flax. Yeah, Flax is a more modern. I mean, you should use Flax rather than haiku. The way to do things is very, very similar. Okay.
What do these do? What do haiku?
It's a neural network library on top of Java.
Yeah, it's a neural. It creates one, and it automatically deals with parameters and how to deal with these things. Okay. And then I like to write tests just to make things run without crashing. So there's a test here that tries to create this field, create parameters for them, and then just try to see the output of the equation looks like what you would expect. The loss function in the next cell is basically defining the equation which depend on the field themselves and saying that this equation should be satisfied in the sense that they should all be equal to 0. So you have the first equation, the second equation that you had at the top, and you also have the boundary condition for psi, which should be 0 on the boundary. So data.
So the loss function is basically the square of each of the equations.
Yes. Yeah, exactly. I think in pins this is perfectly standard to find things like that. The generate data is something that's going to generate a bunch of random points, so you have the interior points and the boundary points. I don't think there's anything really particularly special here. Then again, there's a test that just tries to run up all of these things and see that it doesn't crash. So the test is performing a single step of gradient. Okay, if you really wanted to to run that, you would have to have a for loop that keeps on updating the parameter. This contains almost everything. I think the most important thing that is missing, apart from the for loop, that's easy, is the fact that right now the fields are not being normalized. So if you just run that, the likelihood that you're just going to convert to something where all the fields are 0 everywhere, which is, so you need to normalize somehow your field to say, well, I want something to be non-zero. We briefly spoke about that with Ravi. It's actually not completely obvious how to normalize the field, because you could try to say, okay, this field has to be equal to 1 in the middle. But there's no guarantee that the equation should, that any equation should, any solution should satisfy that. So I think there's still a little bit of work to be done there. One thing you could do is just like choose an epsilon, which is a slightly small number, but not too small, where you define a loss so that if your field, let's say psi, for example, or one of the other one is smaller than 1 in the middle, then you have a loss that pushes towards. But if it's above, then you kill your loss, so you don't care about what happened.
You could also do something like just 1 over
Yes.
the mean of,
Okay, sorry, yeah. That
This is also another possibility.
That's
we
another
discussed.
possibility,
yes.
But maybe in that case, the network is encouraged to get very high values because like it could close up, I don't know, if you.
But of course, you need to hyperparameter tune the components of the loss such that they are.
Yeah, or doing something like kind of in the spirit of what Seth just said. Like if you're very, very small, then divide by that.
Yeah,
So that
I think the loss
and
was
kill it, like above a certain value, then
Yeah.
just kill it.
Are they known to be positive or something? Because then you could just sort of put an exponent around it. And you can learn e to the f.
But most likely because the problem is elliptic.
Yeah,
So,
exactly. Yeah.
so there has to be some underlying maximum principle.
So
But
where
I-
do you put an exponential?
Yeah, I mean, if the function is known to be positive because it's an elliptic PDE,
Yeah.
you could, instead of learning f, you could learn e to the f, which is not
Yes.
0.
Yeah, no, that's a good idea. It's not going to prevent it from going to 0. So.
Well, then it would have to output minus infinity.
Yeah,
Sure.
it's not impossible.
No, it's
That's-
impossible, but it doesn't sort of, it's further away, it's an infinite distance, and
Yes, but
neural networks don't have to output minus
Yeah.
infinity, but
yeah, I mean,
it doesn't,
can
of
see-
course,
I mean, I've seen that the neural network are perfectly happy to diverge, do horrible things.
Okay, I had much more, so, okay. So for me, when I had to learn something positive, this usually worked.
Yeah. No, but I agree that positive, putting the exponential is positive is the right thing to do. What I'm saying, it's not going to prevent it from going to infinity and go to 0. The exponential is going to prevent it from being negative, but it's not going to prevent it from diverging to the trivial solution where everything is 0. That's what I mean.
Yeah, so when I did it in practice, it worked. Without, of course, in principle, it could have still done it. In practice, it didn't anymore.
Okay.
So, but it's circumstantial evidence. Of course, I agree that you could essentially even minus infinity. So
Yeah.
I just in practice, it didn't happen anymore when I exponentiate.
So in the past, when I have worked on problem where you want to avoid a particular solution, either I knew a value of a point or I knew of a stretching property where you know that if you have a solution, you can also multiply the solution by something else so that you still have a solution, and then you can impose the value at a point. You can choose any value you want at a point, and that prevents it from diverging. Here, it's not obvious how to do that. Yeah. And the nice thing to do was the thing that you and I thought about, which is to instead of being stuck to a circle, learn the shape as well of the object. And I think that would be a lot more interesting than what's being done there, because that's the whole point of the conjecture, to say that.
Well, later, no, because this is still in the axisymmetric setting.
Yes.
So in the axisymmetric setting, it doesn't say anything about the conjecture.
Okay.
But as a starting point, like instead of trying to do the whole thing in one sitting, then like as an increasing difficult problem, then one can first fix the domain and work in axisymmetric, then move the domain and work in axisymmetric, and then move the whole.
Yeah, no, totally agree. When you do this sort of thing, you need to start. You shouldn't start with a whole problem, because then the thing doesn't work, and you have no idea which bit doesn't work.
Right. So this is the real reason as to why the problem is somewhat capped in some sense. Like it's not, maybe this little bit is not super interesting, but it will help to, like, for the calibration, for understanding whether the fields are big, whether the fields are small, where does the pin struggle, these kind of things that you test it on like a smaller, let's say, easier problem where you don't have so many moving parts.
Yeah.
So that's sort of the purpose of, let's say, this little part.
Yeah.
But I think in the end, sort of having all these moving parts and sort of having different neural networks for different functions, one also the changes bound, so that they can work in conjunction, find something.
Yeah, but then the issue is whenever things don't really work.
No, eventually I think it's a good thing. I agree. So to start with, you need to sort of see that something works and then make it more and more complex.
Yeah, absolutely.
So what's the expectation? So these are solutions where we just have some sort of flow going around in a ring, right? And then there's a family. There's like any parameter family of solutions, and then they don't have to vanish at the boundary. The normal vanishes, obviously, but the solution at the velocity.
Well, in this framework, the string function vanishes at the boundary, but when it comes to like the velocity is tangential to the boundary. So if you go back to, let's say, magnetic fields or velocity, if you think of it as being Euler, then the velocity is vanishing on the normal component. So you don't really think of it as being a tokamak. Then the fields don't escape the tokamak, or the velocity doesn't go outside of the boundary. So that's the boundary condition.
But the velocity can be non-zero on the boundary.
Yeah, absolutely, in the tangential direction. Yeah, this is what makes the problem harder in 3D versus 2D. So in 2D you have more rigidity, and then using that you can do more pen and paper, and it gives you more rigidity in some sense. Whereas in 3D it's not so obvious, because then you have more tangential directions. That's the issue.
But since there are many solutions, we just expect the gradient descent to converge on a randomly chosen solution out of this, or what do we?
I don't think anyone knows that answer. I mean, in getting any solution, I think it's already interesting. Let's say for a fixed domain, axisymmetric fixed domain, there are, so the solutions that are known are only known in asymptotic regimes. Now, there is now a new paper from maybe 2 months ago or so that I didn't completely check, because it's like, I don't know, 60 pages or something like that. So maybe barring that paper, which I'm not sure, everything that has been found is axisymmetric. And it's asymptotic and axisymmetric. So asymptotic to the domain being a point, like the section being a tiny point, like a tiny filament, let's say. So it is not a pure filament, it is enlarged a little bit, it's a fat filament, let's say. So that's the regime where people have managed to calculate things. So in this case, the section would be like a very small disk. And beyond that, and it's all asymptotic, so there are no bounds, no pictures whatsoever, or no nothing.
But this thing with that looks like a filament, its velocity does vanish on the boundary, or?
You mean the full velocity? I don't think so.
No, okay.
I don't think so. But it would be nice even. So, okay, here's what I think it may happen: that you have a family of solutions, which include the domain as well. I don't know what is the dimension, but certainly at least one dimensional. And then you can follow the branch up until somewhere. But I am under the impression that you can construct large tri just by doing continuation. So one thing that one could perhaps do is, once let's say you fix your domain, you find a solution, then you can perturb the domain a little bit and track the set of solutions doing continuation. I just posted maybe a relevant paper on Zulip, where what they do is to construct these things for a fixed domain, and I think they pick a family. This is the general setup. I think they pick a family for a certain F or a certain A. I have to check, because the equations are not like one-to-one, in the sense that I need to check what does the A from those equations correspond to whatever they use on the paper. But they are making some choices for the scalar functions and solving for the C in that paper, and they using machine learning, and they can get something to a few digits of precision. So what they're doing is solving for a concrete, even a more concrete problem, because they are picking. I guess the F for the field and solving for the psi.
So another, I think, something that would be nice indeed to change in this setup, if you go a little bit down where the loss is defined. So the loss was here, this loss function, is that we have, the loss is a sum of three terms, where so you have the two equations and then you have the boundary condition. So here we are learning to be zero on the boundary. So there's actually a simpler way, and I think a nicer way to do that is to, maybe I can draw it. If you have, if you define like something like a parabola, okay? So your parabola is going to be something which has a non-zero, so that's a circle that's got a non-zero gradient here and here, but you can use that because this is a circle and you can choose it to be unit 1, you can multiply the field, so the psi, by whatever you have here, okay? And that's guaranteed, I mean, that, so if you assume that this is it's a parabola where this is the plane, okay? So that circle, this parabola is 0 on that circle, so if you multiply your psi by this thing, well, you guarantee to be 0 on the boundary by construction, and also you can still learn any gradient of your psi on the boundary because the gradient does not vanish there.
So parabola means you're postulating a fixed quadratic function?
Yeah, exactly. So, yeah. Choose a quadratic function. It doesn't matter exactly which one. You just want something which is going to be 0 on the boundary of your circle, have some nice gradient on the side, and then you multiply your psi by that, and then you don't need this extra loss to learn to be 0 on the boundary.
But this only works if the section is a circle. No? If the section is not a circle, then you either have to change coordinates or do some
Well, depends how you created your section. If you created your section by doing a deformation of the circle, and your deformation of the circle is something that is learned, well, you know exactly how to map that to thing, and you can still do the same thing.
What regularity do the solutions have?
Yeah, the conjecture and everything that people are looking for is symmetry. So it shouldn't. Well, I don't know if this is a bug or a feature, but
Do people like the idea of using like relative neural networks versus the infinity functions?
probably not.
Yeah, so that's a thing to discuss, right?
If we use scalu then for that reason.
Yeah.
I mean, of course, you still don't know whether learn something continues or not, but at least activate. I mean, at least activations are.
Yeah, I use tanh here. I mean, tanh is nice if you know that your function has to be bounded, because it's guaranteed to be bounded. Since you're on a bounded domain here anyway. It would work for Gelu, but if you had an infinite domain.
I would have said polynomials or polynomials plus some kind of.
Polynomials, I think in practice they seem to be very unstable.
If it's a bounded domain, and you know, again, if the thing you're trying to approximate is smooth.
Yeah, all of this is completely empirical. For
It
some
depends on
reason,
it depends on the equations. I mean,
Yeah.
the equations that, like these Calabi outcomes, they work very well, but some other equation, of course, it could be terrible.
yeah. Or so Gelu is kind of a variation on something which is called soft plus. So soft plus is something that goes kind of exponentially to 0 in one direction and looks like linear in the other direction, which is something that works very well. And Gelu just it's got a bump.
But there is a solution.
I mean, something like Gelu is particularly important if you have a very deep network, because something like tanh is going to keep the gradient. But then,
In this sense, there's the same features of Slickery loop, but it doesn't repeat down. It doesn't close to 0, and then there's a bubble. It doesn't talk to y equals x.
exactly. And if you want something that is still bounded, but you want Gelu, you just put Gelu everywhere except at the very last layer where you put tanh.
So presumably, one will start with different initial conditions and just get different solutions.
If we get a solution.
A different initial condition and different training data. All of these things can give you different solutions in the end.
The good thing about this problem is that getting a solution is already good enough. Like you don't need to really So I mean, the more you find, the better, no? But even getting one solution would be very good, especially if it goes like all the way up to the conjecture. Like getting one counterexample is good. But getting 10, okay, doesn't really matter that much.
No, but I mean, on this way, you know, so families of solutions exist that every time you initialize a neural network, you would find different random solution. Or
That's
is there a metric on the space of solutions under which you would say one has a higher, you know?
Nobody knows.
But the real counterexample, again, we need to break the symmetry.
Yes, that is true. Yes. But for example, if
I mean, is it possible to, I mean, you said torus, you know, so I suppose you could imagine a more complicated shape.
that's true.
The domain isn't, like, suppose the domain itself is manual.
Yes.
In RNC, would that count as a counterexample?
Can you?
So it's still axisymmetric, but, so like, there's R here, and then there's this, you know, asymmetric direction, right?
Yes.
Now we're imagining this, but if we imagine this, I mean, you know, the hole in the middle,
Yeah, that's pretty.
and then, you know, there is velocity.
Yeah, no, that's.
Would that count as a counterexample?
I would have to check, but I think that's fine.
You mean a shell?
What is the axis of revolution?
Yeah, I haven't drawn the axis of revolution, but this is R, this is Z, and now we circle around, so now it's like.
Okay, so it's like a hollow.
It's
like
a hollow torus.
I think that's fine, but I would have to check.
So that wouldn't count as a counterexample.
No, I think
But that would count.
if you no, the counterexample has to break the symmetry.
Okay,
This still has a symmetric symmetry.
Yeah, so you count the symmetry as the.
Yeah, exactly. So the symmetry is the attribute that you want to break.
Yeah, okay.
Whether this has a hole or not, I
Yeah.
think it doesn't matter, but I would have to check like the original reference.
So genus 2 surface or something that would work then.
Well, that probably not. Well,
We need more complicated equations. I mean, I guess the next question you could ask once this works is there something where it depends on, it breaks the symmetry, but it breaks it in such a simple way that you don't need new,
right.
you know, new coordinates.
Right.
Think about that.
Yeah, I mean, what I was going to say is that maybe, I mean, I don't know, maybe if there is a counterexample, maybe one is lucky and it's even close to like an axisymmetric one, in the sense that you may have like a bifurcation from a particular profile, which is axisymmetric, in a way that breaks the symmetry, so that the generator of the bifurcation or the tangent vector to the bifurcation is not axisymmetric. So maybe once you have a solution, it's not so difficult to compute, for example, the differential across some of these directions. And if you have a zero eigenvalue, then you're done. So there is, I don't think people have even tried that. This is one of the things that it's, you know, in the back of my mind since I saw this early paper from Gavrilov, that maybe if there is such a good numerical solver or one can produce easily with a lot of codes these kind of solutions, then one can check, because the calculation by hand is not so obvious, because you cannot really. The issue here is that, okay, the paper of Gavrilov is, let's say, difficult to understand, and it's not so clear how the things go towards the limit when you sort of shrink. So that then, if you were to expand based on that and compute the bifurcation or compute the differential, it's not trivial. But maybe numerically, it's easier in the sense that all you have to do is to compute a big matrix. I mean, I'm downplaying it a lot. I know it's hard, but this is kind of maybe a way to get to it. And then, okay, if you can have some evidence for that, then that's it. Because then you follow the bifurcation and you don't even need to be close. So that would be maybe potentially one route of breaking the symmetry. Maybe it's simply enough that you don't need to go to somewhere which is isolated, let's say, from the space of axisymmetric solutions. But this, I don't know. This is, in some sense, a lot of wishful thinking, and I have no evidence for that. But that's what I would dream about if I were to try to go in that direction. And probably one of the very early things that I would try once there is a way to get a solution, an axisymmetric solution in a nice, stable way.
So people didn't just try to solve these equations in 3D on a supercomputer or something.
Maybe for something, as far as I know, nobody has tried to compute the Gavrilov solutions, or for that matter, I mean, there are papers where people compute these kind of solutions, but either they pick certain values of this, or I don't think they are going in the direction of the conjecture. So it's more of like I don't know, testing a solver for the equations on some toroidal domains or things like that. But I don't think, maybe in the early days, let's say in the 60s, people used supercomputers from the 60s to compute these things. But exactly, because people were kind of somewhat interested in fusion, but now I don't know what is the latest status of this. But as far as I know, not many people have tried to use machine learning to solve these things. I posted one reference, maybe there are a handful more, but this reference is already November 2023, so relatively recent.
Okay, so we'll look from your notebook, I guess, and just try to make it work.
I mean, if anybody is already used to Flux, this is just a baby thing, but if anybody is not used to Flux or Jax, at least it's something where to start from.
Should we go into another?
Maybe we can start what we've been doing for the podcast. Sure.
Yeah.
So just how we generate.
Well, or maybe just the reduction to the so the stability. I mean, with the stability in mind, let's say the more attainable goal for this week is to be able to and instead of like computing eigenvalues of the stability problem, even with the reduction m is equal to 0 and so on, we thought of like an intermediate problem, which is to predict values for Sturm-Liouville problems. So because at the end of the day, you can more or less solve and transform your 4x4 system into a 4th order 1x1 system, and it has that kind of flavor. So we decided to start and see if we could be able to predict eigenvalues for Sturm-Liouville problems, let's say, as we change the P and the Q from the equation.
Yes, and right now we have an implementation to find this eigenvalue from a given Sturm-Liouville problem that you give it the functions and it returns the lowest eigenvalue.
So now we can plug it into the transformer model to create examples. Try to see if we can train this.
Mm-hmm.
Similar to phrases of supervised learning.
This is just supervised learning.
So PQ in and eigenvalue out.
Yeah. Well, actually, exactly PQR and then. But then I mean, it's feasible, and then there are other things than Sturm-Liouville, or you can change it a bit in a way, some modification around Sturm-Liouville in a way that works. You could at the end of the day just put equation and then of course that would only cover the classes of system that you can see in the training. But if there are several classes, maybe you can try to see things that are between classes. It's not completely clear.
Yeah, so this is like a smaller class. I mean, ideally, it's equation. You in equation out eigenvalue, but for now we're taking a smaller subset of equations, like just only Sturm-Liouville problems. So in Sturm-Liouville for now, then our eigenvalue, with the intention to build a set out of Sturm-Liouville problems and other things. But for a current time window, Sturm-Liouville maybe doable. So we are at that status where we have the solver and then put it into
The solver, what is the solver?
Yes. So it uses the proof for transformation that allows you to directly find the smallest eigenvalue. So you give it the bounds, and it does a shooting strategy to solve the boundary value problem, and then it uses a range Pluton.
Because that's when we go to 5-7 plus a shooting.
plus some extra additional conditions to avoid like just having a window which is too big. Because if you give it too big of a window to look for, then you may have several eigenvalues and then you don't really have monotonicity, so the shooting may fail.
But these transformations allows you to go for one of the eigenvalues given the index. So we only care about the smallest one, right?
For now.
For now. Well, I mean, it's just changing one value and then you can find whatever eigenvalue.
So there is a little bit of pre-processing in a way that you avoid the situation where the window is too big and then you have several eigenvalues in between and the shooting fails because of that, because you don't have monotonicity anymore. But then when it comes like to the solver, is you integrate forward with a Pluton and then you do shooting on like on the other half. And we will take P and Qs that are not crazy so that we don't have to deal with like singularities and so on. But the hope is that we can put the solver into the transformer and see what happens.
Yeah, I think that's a bit of time to be able to train, interpret, and so on. I hope that we can integrate this into a repository with the transformer by. Okay, say tonight, but then tomorrow.
Well, sure, let's get some.
Then on the fourth problem, following Tristan's instruction and explanations yesterday, so I have put again in the transformer that is, so every time it's a fork of a project that is public repository, so that because I'm listening, so I'm still I can still be reached, but then with the explanation, so how to modify it to put the graph pairing it showed us. So I went back on this collab and wrote this into the environment. I'll do the same for this. Public story. The first one is mine, and one is a Facebook repository, but it's on the public side. We have updated code actually with François Charton, but I can't share it as long. I mean, I can't share it either as we will just we need a bit of time so that Meta uploads. But it changes just details like that would fasten the code by 2. So it's not a fundamental differences.
Some updates on the other problem?
Yes, go ahead.
Yeah, so I've thought a little bit and written some code for the calibrated geometry problem. And effectively I've done the simplest possible thing, which is making sure that I can flow a T3 embedded in a T6 to the special Lagrangian representative, which is the flat one. So that makes sense. And then so there's the question that you posed on the Zulip of what can we do about two intersecting copies of T3. And so there's obviously a way that you can embed one T3 into T6. You just train a neural network to learn that embedding, right? take the T3 and put it into T6, and then minimize something that corresponds to pushing you towards the special Lagrangian submanifold. It's slightly harder to do for 2 copies of T3, but it should be possible. Essentially, like, I think I have quite a good understanding of how you could do this problem in 2 dimensions, i.e. with two copies of T2, because you can, the smooth version of joining 2 T2s together with this Lawler-Neck object is just a genus 2 surface. So you could just learn an embedding from a genus 2 surface into T4, and then find the special Lagrangian representative of that. And we know exactly how to do that because you have nice algebraic representatives of that genus 2 surface. For T3, it will be slightly harder, but something analogous to that should be possible. It just might not be that you can just use it like a defining equation in the same way that you would for the T2. I haven't really finished thinking about that, but something along those lines should be possible. So effectively, the topology of the manifold we're trying to learn is just the connected sum of these 2 T3s. Like it's pretty simple. And the Lawler-Neck, this object introduced and discussed in these papers, just does that gluing for you. And so, yeah, as I said, I've written the code to embed T3 into T6, and it's really straightforward, and it works. So something analogous to that should be able to find the equivalent version for the union of 2 3 tori. There is a slight question about this angle criterion, which I think, yeah, will be interesting to work out. When you don't satisfy the angle criterion, does the topology stay the same? I guess that's something.
If there's only that point of intersection and you don't satisfy in principle, it should be stable. Yeah.
So what should
if you really literally intersect 2 special Lagrangians, and at every point, you satisfy the angle criterion, that really should be a stable thing. The union of those 2. Yeah,
right. I guess they only intersect at the transverse point. Right?
Yeah, that's right. If it's not transverse or more complicated in some way, then who knows?
When you put this Lawler-Neck in, it still has this quite simple topology. But if you start flowing it, I guess we have to, the network will be designed to embed a certain shape, certain.
You say a little more about the T2 case. So the idea is we start with some given embedding of, say, the genus 2 surface, and then we put a function on that to say how we've deformed the
precisely. Yes.
Okay.
Exactly.
So now we're looking for the T3 version.
And the point is that embedding into T6 is totally trivial, right? You just take the mod at the output, and that will learn a function into R6. As long as the net function we learn is smooth, then this will be an embedding. Well, it'll be like an emoton or whatever, but you can hopefully test whether or not it's an actual good embedding, which is what we want without it.
Okay.
I was going to ask about this embedding. You have to. I'm sorry, I don't understand really the problem, but you have to learn the embedding, right?
Yes, that is what the network would learn. Yeah.
So how do you actually make sure that things don't cross each other, for example? Because there's no reason why the neural network can do that, right? How do you check that, and how do you encourage that?
Yeah, so I guess that's absolutely a problem, right? But the hope is that this case is simple enough that it won't want to self-intersect, but you can test similar. Well, one thing that you want to test is the curvature of the embedding to make sure it's not getting a kink or something. But you can also imagine trying to. It's a simple enough case you can probably start plotting things and looking at it to see if it's self-intersecting. But yeah, the simplest thing to do is just to run the flow and see what happens, right? And work out whether or not it's self-intersecting from there. But yeah, there's probably some more complicated, more sophisticated tests.
But there should at least be a computation to look for the intersection. So
yes. Yeah, of course.
Yeah. So what we thought about doing in such a case was you add essentially a repulsive term to the loss, so that if it was to intersect in 60, it would repel.
You could, but that would be really expensive, right? Because it would have to look at any variable points. It'd be like this knot thing.
Yeah, that's exactly. So we triangulate the surface and then
that's what we did for this not functional, but now it's pairs of points.
Yeah, of course.
It becomes surfaces.
That's too expensive, exactly. But hopefully, I think just looking at what this Lorlanek object is like, it's simple enough that you can probably visually understand part of some of the flow, especially with the symmetries of the problem. Like as long as the flow that you generate respects these symmetries, which it may or may not, but you can test that. It should be, we can just try it and see what happens.
If we get a self-intersection, it could be these allowed self-intersections. It's not obvious because it's a high dimensional thing, but it can be that two of these planes that are locally like planes crossing, and you actually can't reconnect them the way you could reconnect a one-dimensional. Like two lines cross, you can always shorten it, but that turns out not to be true in higher dimensions. And so there are some allowed self-intersections, and then if it's not an allowed self-intersection, then you could complicate the ansatz. Like our starting point was two things. We know something's crossing here, so we embed this more complicated surface and things. So now if we discover now it's crossing someplace else, we could embed a still more complicated surface if we had to. But we would have to know that it's self-intersecting.
Sorry.
I was going to say, here's an idea to try to learn things that don't self-intersect. If you have like a database of things that self-intersect and don't self-intersect, learn a predictor like a classifier, and then use this classifier to create a loss which tries to predict that it's not self-intersecting. So then you have a proper loss. Hopefully, if it's a good predictor, then you have a loss that encourages things to not be self-intersecting.
Yeah, that's kind of a separately interesting thing to try to learn to see if that can be learned.
Yeah,
I agree. Yeah.
But it's not just about learning. It's about you don't care if the thing is really good at learning. What you care is that you need to have something which is relatively good at differentiating the two things, and then you have a nice loss to say. Encourage things to have a classifier where it says that it's not self-intersecting.
Well, yeah, that's right. We have that application in mind, but these intersection numbers are actually very interesting, even independently. That's just like when you make these things, then this would be like the starting point to say there's various things you can do. But I think that string theorists do is you postulate these branes in the extra dimensions, and you say we want to get out the standard model or some kind of physics, and then every place where it intersects is some place where there's quarks or leptons or some kind of matter. So it's already interesting just to know how they intersect.
But it sounds like so in this case you just described it even harder because you want to learn where the self-intersections. Whereas what I suggest is just something that predicts.
You don't in principle have to. You might want to, but just the fact that it intersects, just to count the intersections is already interesting.
Okay. Yeah. So my bet, if I had to bet, is that learning is something self-intersecting as something as simple as an embedding of a genus to surface. That should be trivial. Okay. I'm ready to bet money that this
that's very plausible.
Well.
That's very plausible because it is kind of a topological thing.
Yeah.
The only challenge is again we through this representation of the embedding, but maybe other times we would. Yeah.
I was actually going to ask maybe to elaborate more in that context because I tend to think of the calibration question as just orthogonal to the topological question with respect to the physics, just because it is topological. But is there something to be gained from learning about the intersections of the calibrated cases?
You're saying, I guess maybe I should have been more careful in what I was saying because there's like a plus and minus one intersections, and the thing which is topological is the sum of those. So like you can imagine, So now from the point of view of geometry, they do intersect. Right. But from the point of view of topology, they don't really intersect because you could have split the one off the other, and that's because the one intersects is a plus one, and the other one's a minus one, and all those things are actually interesting to learn. Yeah.
Maybe one more.
Sorry. I was saying this loss function thing, might well be a good idea for the case of an embedding into more complicated manifolds. But in this case, it's hopefully simple enough that we don't need it. But
I was going to say that for the classifier, this classifier RD, you really want to do early stopping in the classifier because if the classifier is kind of perfect, you end up with a step function, and you're not going to get any gradient whatsoever from that, right? So you want to have something which is a little bit smooth and not perfect, but kind of like goes to 1 if it looks like it's not self-intersecting or the otherwise. So early stopping is good.
So another thing we thought about was to use an invertible neural network to do the embedding. Because sort of if it's self-intersects with different points in the original surface are mapped to the same point and embedded. So this sort of means it wouldn't be invertible at that point. So you might just, so I mean, yeah, people have worked for a long time on sort of, just writing down invertible neural networks, so that might prevent this as well.
So is that how do you do?
Just learn an invertible neural network. Ensure that the neural network is learning an invertible
But I'm not sure I get it, because your function is going to be a function from from a certain surface, certain genus into something of a higher dimensional space.
Yeah, but
so that thing is not going to be. So
it only needs to
like
be
an
or
something like that.
It only needs to be on the image. You don't need to worry about the rest of the.
Yeah. So this will be from the embedded surface in 4D into the embedded surface. I mean, onto the surface. This map has to be.
This, I agree, but it's not really clear to me how to do that.
Yeah, I mean, you might also worry though, if the dynamic wants it to intersect, it's just going to slow down. We'll just asymptote towards the intersection. It's not like you got rid of it.
Sure. But I mean, it couldn't learn, but yeah, it might not convert. Yeah.
Also, Fabian, do you know of an example where people have done this? In the sense that, okay, I know of invertible neural networks or something, but one that's invertible on the image, that's not something I've seen.
I mean, the other thing I would be worried about is that the intersection kind of has, I mean, I'm not sure how you would do that, but you could, if I understand well, that you would take things from the image and you would try to learn a neural network that goes back to the original one. But the intersection typically has measure 0. So that's going to be kind of hard, because for most points, you can invert it. So if you train, if you try to train, and you have to choose a finite number of points when you try to make sure that your thing is invertible, the probability of finding points which are 0 is 0.
Yes, I know.
So I don't fully get how to do that.
Well, I mean, the problem is also with the classifier. You give it a bunch of points, it will always sort of say they don't intersect, because you're not sampling the measure 0 set that they do.
But now with the classifier, it's easier, because you create your data set yourself, where you know that some things are invertible, and you create cases where they are self-intersecting. So you create it on purpose to have that. Whereas,
yes, but then for this thing to sort of see this from a, I mean, the problem is not even unique. If I give it points like this, I don't know whether the curve was this, or whether the curve was this.
But that's my point about like learning an invertible.
Yeah, but also, I mean, when you train a classifier, what do? You give it a bunch of points. So the classifier would then have to classify what this.
Depends on your representation too.
Yeah, so how do you represent?
You represent it as a like a basis expansion of the function, of course. But you do represent the function.
Yeah, you can do the classifier given the weight of the network, for example. Not a bunch of points from the surface. I totally agree with you that if you have the bunch of points from the surface, yes, you have exactly the same problem.
Yeah, that's probably not the natural thing.
Yeah, but if you can do it from the weight of the network, that, okay, I go back on what I said earlier. That's probably a little bit harder, but in theory, it would work.
How many, I mean, on some level, like interpretability, but I'm just trying to think, probabilities works where people do that. They take the actual weights of a general network and they interpret it. They try to learn things about the function. It's very rare.
Yes. That's why today I'm backtracking about this.
Yeah, 10 billion.
No, but you wouldn't use it.
Yeah, you wouldn't use it.
1,000 or 10,000.
No, but it's a kind of an interesting question. Like, can you detect some topological thing about the function?
I agree, but I don't know many papers.
Maybe that's
by many
independently interesting thing to work on.
The question of how to make the weights and make it interpretable.
It's sort of like interpretability. It's
well, in some sense, but
you have a network that parameterizes the embedding function. You give the function to a classifier in the sense that you give the weights to the classifier.
Yeah. So it's not even interpretable. Like you don't.
And then you just ask it, does this produce something that's up?
Well, I mean, I guess the simple question like this is you just have the network representing a function, and to what extent is it a Morse function? You know, how many
Yes.
critical points does it have? Can one learn that?
Yeah, this is getting very complicated.
It seems also interesting.
But it's an interesting project in its own right.
Mike, how much do you know? So this angle criterion that you mentioned on the computer, I've read a bit about it. But it seems to be saying that the angle criterion is always satisfied in complex dimension 3, which would kind of be
No, that's not the case.
modulo orientation. It might be true.
Yeah.
If you allow either orientation for your two planes, I think it might be accurate.
Yeah, if you allow either orientation, let me think.
Which means that there is always this sort of family of special Lagrangian manifolds which converges to the singular union, the cone.
I thought in 2A, the angle, you're talking about like the angle condition 2A. I thought it was an extra condition beyond just the special Lagrangian nature of each of the two intersecting.
Well, there's an angle condition for preserving supersymmetry.
Exactly, yeah.
And then as you move away from that, there's, I mean, in physics terms, you know, one direct, you're giving mass to this, you know, scalar, you know, field of the string between these things, say, and then one direction will make it tachyonic and the other will make it massive. And now the question is, what makes it chiral? So if it's chiral, then only one of those guys will exist.
But in my recollection, it's a non-trivial condition. It's not just a question of orientation.
Well, there's, it's been long enough, I'm afraid, to not have it at my fingertips. I think he's right that, you know, if you don't care about the orientation, that, you know, one orientation will have this, but then physically you do care about the orientation.
Okay.
And so then you can kind of enforce the condition, but as a geometric problem, maybe you can't.
Yeah, that's like.
No, I'll check it. I should know. Okay, so those are all our problems, I guess.
I've been thinking about a problem that is not in the list that deals with general flows of geometric structures and how machine learning can help predict it. So talk about it a little bit more.
Okay.
I think maybe it's easier if I show this screen.
I mean, in physics, a brain is different from an anti-brain, so that's the basic.
Quite different.
The single criterion was somehow related to wasn't it all the
No. Well, I mean, the fact that they topologically intersect leads to this chiral matter, and that gets related to atomic cancellation.
Yeah, but wasn't it?
But then this is a continuous thing, you know, the actual orientation of the two planes.
Each D6 frame gives you an n=1 subalgebra of n=2, and you want to make sure it's the same one.
Yeah, that's the equality there.
Exactly.
And when you move away, you get that thing that would have been a massless state in the supersymmetry case. It either becomes massive or tachyonic.
Yeah.
So the first disclaimer is that those slides are not mine, and I'm not expert in this. I've been starting to.
So whose slides are there?
From Henrique side.
Okay.
It's my advisor. But basically the idea is that the problem is we have like a geometric structure and we want to evolve it in a certain way that it stays in the same cohomology class. And the main question is what is a good flow to consider. And basically so is everyone familiar with the notion of geometric structure? Or so basically, okay. So basically, you're considering you take a frame bundle, and we say that an H structure basically is a section of the quotient of the frame bundle. And the way I like to see it is that you have a tensor. So you have a tensor like this, and you defined geometric H structure by the isomorphism. So basically, you can take I mean the things start to be interesting. And
Sorry, can you go back?
Yeah,
Still
sure.
digesting. So H is a subset. I mean, it's of the frame bundles, and no, H is a sub-bundle of the bundle of isomorphism in each of the. And then you take the quotient of
certain group H.
So okay, so the frame of M is all of the GLN of the thing, and then you take the quotient. So
H is a subgroup, so it's like saying,
yes,
you can already just think in flat space. So like a complex structure, you know, if you have R2N, you know, the basic example. Now, when you think about that as CN,
yes,
R2N, how you impose this additional geometric structure, then the proof theoretic way of saying it would be that you found this UN subgroup in SO2N. You've picked out that special subgroup, and you're only going to preserve that, and that's the H.
Yeah. Basically, you want to. I mean, you have like this H invariant structure that defines it, and basically, the idea that I think later will be more clear. But what is interesting here is that these H invariants have some action that's already defined. And basically, the nice thing is that any flow of an H geometric structure can be induced by this diamond action. So we have like a two tensor that lives in this space, and these two tensor parameterized by this action, any flow. So the question, the interesting question is, okay, we know where A lives, but we want to describe this matrix, this tensor, right? And you can pick basically, I mean, any geometric structure that you like. So here's the example, the simple example is O2. So you can define the flow, I mean, the second order invariance of the flow can be described this way. And basically, this is the general equation of the evolution of an organic flow. The case that I'm interested the most is the G2 case, where you have like a 6 parameters family for the G2 flow of a G2 structure. And the takeaway lesson from this is that basically you can take P7, whatever you like, and you can explicitly construct a family of parameters that describe this flow of this geometric structure. So right now, what I've done, I've implemented this actually. The question is, okay, you have like a family of parameters, and you want to study like a long-term existence, and you want to study.
You're just going to metric. You're not.
Yeah.
Okay.
So we have like a family of parameters, and want to start to ask a lot of you want to ask interesting questions about convergence and long-time existence and solitons and stuff like that. So.
So how do you represent your metric in your manifold?
Maybe I think I can do an example of. Can I?
Yeah.
So let's put the simplest construction and we'll do it. So I have a Calabrial threefold, and I can construct. The way I can induce G2 structure here is by the pullback of the Hilbert form, where capital omega is the bottom form. So, for instance, what I did was this can be numerically obtained by Donaldson's algorithm. Doing the pullback upward, these among a set of sampled points on your Calabrial threefolds, you can construct relevant. You can construct.
So omega would be these two.
Yeah, omega is a volume form as S1.
Yeah, no, I know,
Yeah,
but
it's
you're representing it as the way Donald said that is this.
Yeah, yeah.
Metric on this.
Yeah. It's the simply pullback of the.
Okay, got it.
So this is my defined G2 structure, and I have the general evolution. I have the general equation for the flow of a G2 structure, which is right here. So let's pick the easiest case. So this is the general equation, but if I pick everyone to be 0 except lambda 2, I have the so-called Laplacian flow of G2 structure. So basically, I'm saying that at time 0, my G2 structures is using reduces 1, and at time t, where this is the Hodge Laplacian.
Are you?
Induced by the G2.
Can any piece of structure phi be written as a little omega, big omega, or is that an intersection?
So, say again?
So you've said that you start off with a G2 of 3.5, right?
Yeah.
And you got it from the Calabi-Yau,
Yeah.
by the way you wrote down. And then now we're going to start flowing it.
Yeah.
And does it still have that form for a different little omega and big omega, or does it take you out of
No,
that class?
no.
So
That's the question.
So how do you represent it then?
How you represent the
After it flows and it's not of that form.
it is staying the same cohomological class, so it continues to be a G2 form. So what I'm interested to do is to study the torsion components, how the torsion components of it evolve the time. But it is still in the same cohomology class of the initial one. So it not has this form, but it's staying. It stays at 3 times.
But do you represent
it stays in.
But do you represent the difference of the new one and the original one, or how do you represent it? I mean, I'm not saying you can't do it, but I'm just wondering how you do it.
How I represent? I think that I did understand.
Well, so like you more or less define phi sub t, right?
Yeah.
Phi sub 0 is that thing up there.
Yeah.
Phi sub t is what you get by flowing down.
Yeah.
But then you told us phi sub t doesn't have the form of phi sub 0, so you can't represent it the way Donaldson did.
No, but this is just the initial condition.
Exactly. So how do you represent phi sub t?
As a
in the computer. You know?
Yeah, as a true tensor, the 3, 3, 3.
Oh, so it's just a general,
It's a
general tensor.
Yeah, it's a general tensor.
And then do you have like coordinate patches?
Yeah. Because the trick here is, of course, you have to discretize these at some point.
Yeah.
So basically, this is the continuous version, but the discrete version, basically, you have like 5 in t equals 0 equals that. And let me call it so basically, yeah, the discrete version of this flow is basically given this initial condition at some time t plus 1, you consider the derivative, the Laplacian in the direction of the previous iteration. So you have like a cloud of points. At this time, you pick like a neighbor, you select a point and you evolve at a given point.
And then you represent it really as a general.
It's a general.
I mean, you know it was D or something, right? But you're not using that.
Yeah, it will be a 777 already. I get that.
Wow.
It's a non-pi 777. The end of the day. Is a fix. But it is still, I mean, the important thing is that it is still in the same cohomology class. And this was basically me. The discretization of the flow.
So what were you able to get it to do? I mean, so I think, I'm impressed. Let's say that. So what kind of result did it lead to this flow?
I was able to run a few iterations of this discrete version because basically to compute this operator, you have the two main questions is how to compute the hot star induced by the two metric and the exterior derivative that is independent. This is easy, but basically it's just the Levi-Chipta tensor of a metric induced. And for those that are not familiar with G2 metrics, we can induce a Riemannian metric on the product manifolds very naturally. So the Hodge star is easy to do. The discrete derivative is a little bit trickier. There are two main ways you can discretize this. One is by taking finite differences around the neighborhood. So basically you pick one point where you want to compute the evolution of the flow and you pick some 7 simplex around it. And basically you compute finite differences of the forms, but this is not the best way. The best way is to see the exterior derivative as the infinitesimal flow of the G2 form acting on the 7 simplex when you change a little bit, when you change the direction of the simplex a little bit in the direction of a vector field that moves orthogonally to the tree form. This was very hard to do, but this is very computationally expensive. In the sense that I've been able to run like 5 iterations of this and then I complete the problem. And now, this is a paper that, it's a work in progress, but hopefully the paper will be out soon. But the next step is picking this family of parameters. I want to study what is the best family of these lambdas that provides the flow some desirable properties, in the sense that by the end of the day, my dream is to picking any initial G2 structure. I want to evolve it to a G2 manifold because having a G2 structure is not you have to be torsion free, right? So we say that G2 autonomy, if and only if the G2 structure is parallel, right? I'm sorry.
Right, Thomas, your structure is already torsion free modulo your Donaldson, finiteness of your Donaldson algorithm. Right?
No. It's a co-closed structure in the product, but it's not torsion free. They started one.
One you've written down is an SU3 structure.
The initial, you're right. The initial one is torsion free, but when you evolve it, you don't have a guarantee that.
Sorry, the Ricci tensor, you're evolving it according to lambda 2 flow, right? And that the Ricci tensor therefore is 0. Are you saying correct? You pick a general bunch of lambdas, but clearly, for this case, everything is.
If your goal is just to find one, you started with one, so
exactly.
You want a different.
Yeah. Sure. But the question now, of course, this is basically a demo in the sense that I wanted to discretize an easy one. Let's say that the question, let's say the semi-supervised way that I think machine learning can approach this is find a family of parameters that guarantee some nice behaviors you want in any flow. In this case, I picked G2 because I like G2, but you can pick SU2, SUN, SP7, whatever you want. And you have a description in terms of this family of parameters.
Concerning the derivatives, we tried something similar for Calibrated metric. And then, so what we tried there was essentially you train a neural network to learn phi ti plus 1. So you sort of study. So you turn to the supervised task of phi ti plus 1 is just sort of deduced from the right. You compute the right hand side and then you do supervised learning task.
I see.
And then you use autodiff on this neural network. To get the derivative.
Yeah, I complete a bunch of iterations and that fits. Okay. Right now I've been able to run like only 5 because you were saying that you trained a neural network to do this step?
So I trained a neural network. I compute the right hand side from a given starting point.
Okay.
And then I trained a neural network to produce the right hand side of this equation. And then in the next step I just use autodiff to compute the Laplacian.
Mm-hmm.
I get a new set, I train a new neural network to then be phi t plus 1 essentially, and then I...
Because you're using again, a network which is a function of the coordinates on the manifold. Right.
Yeah.
So that you can just differentiate, but you're representing things in terms of the values on points.
Yeah.
So then it's harder to differentiate, but that's why we use networks that are functions of the coordinates, so we can differentiate.
What are these spice functions?
These files? This is the three forms at some point at.
So there's also functions of points.
Yeah.
What is the difference?
Well, so you're representing as a network with, what's the input of the network?
The input of the network, I mean, I tried a lot of stuff, but by the end of the day, the input of the network is a sequence of VTIs, for example.
So again, you have a network which is representing a function on the manifold, and then so you feed in the coordinates of a point, and it gives you the value of the function at that point. Is that what you're doing?
What I'm doing is giving basically the initial condition.
Yeah.
I try to predict what the NF, the final iteration of some very large number of iterations will be, and if it has a long-time existence.
No. I'm just trying to understand some more basic point of what does your neural network actually do? So does it take in? It could take MT. It could take in a coordinate which labels a point.
Oh yeah. So it takes the point on the this guy right here.
So it takes the coordinates of the point.
Yeah.
And it puts out a value.
Yeah.
Okay, so then Fabian's saying, why not just, if you were going to compute a derivative, why not just differentiate with respect to the coordinates?
Good question. Yeah, I didn't try it.
Well, that's the simple.
That's what we do.
I tried the hard one.
Okay.
Yeah, because then
Yeah.
there's no problem pushing this past 5 iterations. So you just have a minute of training, then you get something that predicts the right-hand side reasonably well, you do auditive, and you just rinse it.
I missed the answer to the question. You're starting with something torsion-free already. What is it you're trying to flow towards? I understand why you would want to, if you started with something that wasn't torsion-free, you would want to flow towards the torsion-free point.
Yeah, it is still torsion-free. I mean, but when you pick like different construction, because this is the dumbest one.
Yes.
But when you pick like a G2 over Calabial links.
Okay.
So basically a Calabial link.
Yeah, there are a lot more.
There are more interesting.
I can see how if you move beyond this, for example, the twisted connected sums, it becomes very non-trivial because then there's this natural G2 form in the neck, and then that thing is not torsion free, and then you want to flow towards that.
So this is like the warm up.
Yeah, this is the warm up, but I mean, more
in principle, it should just not flow if you put it in that.
Yeah.
More intense cases, basically, this pullback will give you like a co-closed G2 structure, not a torsion free one, a co-closed, but then you want to go to a torsion free, hopefully.
Yeah, I see. And in more complicated cases, you will not be starting with initial data that's already torsion.
Yeah.
Have you thought about, I mean, this is very close to the twisted connected sum story. If you take another half and glue, have you?
Yeah, I've thought a little bit about it, but I didn't.
We didn't get that far, but we certainly started down this road and talking back with Simon Donaldson, who emphasized that it was already interesting on the 7 ball. You don't even need the topology and all this complicated stuff. That just a question of what do torsion-free G2 structures look like on the 7 ball is quite non-trivial. So what boundary conditions allow a G2 structure in the interior and so forth, and so that might be an easier version of the problem.
Yeah, sure. That's it. But anyway, I mean, I hope I didn't get too chaotic, but I mean, there's other flows and other geometric structures. So basically, this is a paper that just got published, and I just started to study it. I confess that I don't understand all the details involved here yet. But the idea is that you have like a concrete framework to parameterize all the families, and you can pick whatever flow you want, and you can do like a similar procedure to try to investigate.
Or even this G2 Ritchie flow is pretty interesting. I don't think there's lots of things people don't understand about it.
And the result you're saying is new is the 6-parameter family of flows. The fact that it's a 6-parameter family is for 2023?
Yeah. You have also a result for the SU2 case.
Yeah.
So it's a 7-2 parameter family. the flow. Oh, I'm sorry. Yeah, and this is the harmonic region, right? Has this. It's like this.
What is A sub I?
I'm sorry?
What is A sub I and what is the under this summation?
This is basically the direction, right? The coordinates. So this is the harmonic part, the region. This is the first term, the first order terms.
Which is some fourth normal basis.
No, I'm sorry.
Well, I mean, so Richie we know,
Mhm.
and then the next term is some Lie derivative.
Yeah.
J is a complex structure.
Yeah.
Okay, and A is.
As I understand, there are some bases on the.
So they parameterize the hypercomplex structure.
Yeah.
So why is the sum from I equals 1 to 2 then, not 1 to 3?
Yeah.
No, the other sum.
It seems a typo again. This.
Okay, good.
Yeah.
So it's coordinates on the sort of for each of the AI.
So AI are three functions whose parameterizing S2 of complex structure.
Yeah.
So this way is something.
Yeah.
Okay, got it.
Okay.
And again,
Okay, I understand.
So, yeah.
Okay, yeah, it's interesting stuff. Well, we advise computing the derivatives through Autodesk.
Yeah, we'll try it.
Okay, I mean, if you want to, I think we see what you're doing. And, if you want to either share or ask questions about, the results, it is a thing that we kind of
We thought about this.
Yeah.
But, so you actually being able to implement like a bunch of iterations of the flow.
Yeah, so there's no bottleneck to doing. I mean, you're retraining the network after every step, and you just compute it Laplacian with Autodesk.
But so basically, we're doing a composition of neural networks to predict execution directions.
Yes.
Yeah. But okay, so at each iteration, have you measured the numerical error by computing the torsion components of the GTO structure?
No, I wasn't doing this for G2, I was just doing this for
Okay.
Calibrated, and then I was just looking at
Well, there's this kind of complicated SU3 structure thing with more tensors, which they did do, and it's very much like that.
Right. Because I see a way you can like include like because by the end of the day you want to guarantee like torsion freeness according to the flow. So maybe we impose a loss function that's built in the torsion components in the sense that to minimize the numerical error of. I think this can be a nice approach. Thank you. I don't think about it.
And then in physics, there's this kind of generalized family of these things with a few more tensors thrown in that come out of supergravity. And then you get other flows and equations that have very nice properties. So that's also, once this works, we can tell you about some of those. Okay. I'm wondering if we have there's normally on Wednesday a member seminar, and I sent around this notification that we weren't sure. But I got a message from Dan Fried. I think there is going to be, and then there will be lunch upstairs if there's a member seminar. Well, he says one way or the other there will be, so that means there will be lunch upstairs. Okay, that sounds like we've made lots of progress. Okay, so
this Morse function idea is very interesting in its own right.
yeah, I think it's, I've never seen it. It seems like such a natural question.
Yeah.
That's
So trying to predict intersection.
Yeah.
What I was thinking is that for the intersection, it doesn't have to be perfect, because if the aim is to predict the classifier, then, well, the difference between the left one and the right one just means that the classifier shouldn't be very sure about what it's doing. And then if you use the classifier then as a loss, You're just saying that, well, I'd like to find things which are far away from that. Now, maybe it will take you away from things that are really interesting, but
close approach is necessary, then you won't find it. Of course.
like, I don't want things like that.
The force function has the same thing, because you can add a little bump, to a function and get canceling things, and so that's the case where it should not be too sharp.
Yeah.
It's very interesting.
Okay, great. Okay, I think we'll call the discussion for today. Okay, thanks, everybody.